Okay, well, first of all, let me thank the organizer of the meeting for the invitation. And actually, I haven't seen a meeting in person for good part of the year, and so I'm really glad to see people around. And so most of the talks are online right now. Hopefully, situation going to change. Okay, so I'm going to talk about basically a old problem. It's a half-century problem with a new approach. It's called a large moment effective theory. So I'm going to give a very brief introduction to Partons and mostly textbook material. And then I will talk about Partons in Minkowski formulation. That is what the textbook usually teaches us. And then I will talk about going back to the Feynman's old idea, that is the partons in the infinite momentum frame. It is actually the states, not the operators, which define partons. And following that, I'm going to introduce this new approach called a large momentum effective theory. And I will give you some applications, which actually there have been a lot of activities in this area, particularly in lattice QCD calculations. And we've written a long review paper on this very recently. So let me give you a very short introduction to Partons, and everybody appreciate very much Feynman's language, and he introduced many popular concepts, starting from Feynman diagrams to path integrals to Partons, and one cannot do high energy scattering without Partons. In fact, Feynman gave a series of lectures on strong interactions around 1986, 1987. And recently that someone posted all these lectures online. And I was one of the fortunate person that actually was in Feynman's lecture about QCDs. And so I learned quite a bit from his approach to strong interactions. So Feynman-Parton model in a nutshell is to approximate a proton traveling at near speed of light by the one that actually travels at speed of light. So in this case, you would have energy and momentum equal to infinity. And that's why the people introduce the concept called the infinite momentum frame. And in this frame, the proton may be considered as a collection of interaction-free partons, okay? So this is, again, very elementary in every field theory textbook right now. So every parton, in fact, has infinite momentum. And we call it K. The ratio of this infinite momentum parton with infinite momentum hadron is finite, and in fact, it has a limit between 0 and 1. And you introduce the parton distribution f of x as a probability of finding partons in the proton and carrying x fraction of the momentum of the parent. Now, the PDF is a bond state property of the proton, and it is essential to explain the results of high energy collisions. And for example, at LHC, you apply two protons extremely high energy and looking at many different sub-processes. And you can derive so-called factorization theorems. And those theorems state that the cross sections can be written as convolution of these parton distributions with parton scattering cross sections. And so essentially every processes are analyzed in this way. Now, this is one of the success of LHC program. And what's shown here is the various kind of sub-processes with cross sections, which labeled in the horizontal axis, varies by 13, 14 orders magnitude. And you can see that there are lots of processes, starting from jets, photon production W and Z, then all the way to very complicated processes with several W and Zs and gammas and jets, etc. Now, what's amazing is that if you compare the predictions of standard model theory with the experimental data, and the ratio showing on the right-hand side is very close to 1. And so that's why I said this is a great success of standard model, but only partially, because in those predictions, the Parton distributions are not calculated from standard model or from QCD. In fact, they're obtained from phenomenological fits to cross sections. And people have been doing this for 50 years. And shown here is the Parton distributions, gluons and up and down strange quarks as function of Feynman X. And they're determined to a pretty good accuracy. And so these has been used in the prediction of the previous slides. So an important question is, can we calculate this from the QCD theory, from the standard model? So I'm going to start with a story about partons in the traditional textbook, also in terms of Minkowski formalism. Now, how does an object look like when traveling at the speed of light? This question was first taken up by Steven Weinberg in the field theory context. In 1966, he started a scalar field theory showing that how things work when you have a frame traveling at the speed of light. He called it dynamics and infinite momentum. And he found that all infinities, kinematic infinities, can be removed from the calculations, resulting in a set of rules for Hamiltonian perturbation theory. He called it old-fashioned perturbation theory. And so he had a bunch of rules. We call them Weinberg rules, how to calculate things in the infinite momentum frame. And subsequently, people like Susskind, Bardaki and Halpin, all those people, they explore more in field theory context how this rule works. But a crucial development happened in 1969 after Feynman proposed the Parton model, and particularly Chang and Ma studied how does QED behaves in the infinite momentum frame, and followed by Koget and Soper. And they studied the same subject, essentially. And what Chang and Ma discovered was that all the Weinberg rules in the infinite momentum frame can be obtained by quantizing the theory with the new coordinates, the x plus and the x minus. They're combinations of space and time. Space is the direction where the hadron is moving. And the trick is that you're gonna quantize using x plus as the new time and x minus as the new space. So if you look at this coordinate here, you have time vertically and space horizontally, and then the new time is actually going towards to the upper right hand side, and the x minus is the new space. And I'm going to call the direction P for the new time, and the light cone space is direction called N. And subsequently, actually, people discover that the Weinberg's rules exactly corresponded with what Dirac proposed in 1949. And Dirac wrote a paper in Review of Modern Physics in 1949 called Forms of Relativistic Dynamics. And he actually proposed 3 forms that in which you can do the dynamics. And one of which is called a light front form. And so this is correspond to what people call light field quantization, or LFQ. Now, the Feynman's Parton model was proposed in 1968. And his model was formulated in terms of infinite momentum frame of Fubini Plan. He did this not exactly in the context of quantum field theory, but with quantum mechanics and relativity in mind. Okay, he did not have a field theory model for that. However, immediately after Feynman proposed this, the connections with light field quantizations, light field coordinates was recognized. And well, there are two, I think it's good and bad. Well, the good thing about this, now you can do Feynman's Parton model without kinematic infinities. You can just take Dirac's light field quantization and you have a ready formalism there for you to work. The bad thing is that the theory in light field quantization is notoriously difficult to solve. And people have been trying this for many, many years. And some of the people who really championing this, including Ken Wilson and Stan Brodsky and many other people. The main problem of this light field quantization is we have also slow moving stuff. You know, you have a hadron moving at speed of light, but there are also slow moving modes, one of which is the vacuum. And the vacuum, you know, it's a slow moving stuff. And in fact, the vacuum contains the only degrees freedom we call zero modes. And second, it's still a strongly coupled problem. And choosing a new coordinate doesn't mean the problem, the strong coupling goes away. Ken Wilson in later 1990s proposed that maybe there's a weak coupling expansion you can solve. So people have followed that path, but haven't really got any concrete results. Main problem is that there's no controlled approximation. Again, it's a strong coupling problem and it's hard to make approximations, but nonetheless, there's a bunch of people around the world and still dreaming to solve in the light cone, QCD using light cone quantization. And as you can see that every couple of years, they're gonna have a meeting. This year is supposed to be a meeting in Korea, and due to COVID situation, it didn't happen. Now, if you look at the textbooks, this is a 600-page textbook by John Collins and talk about partons or factorizations in QCD. And people usually use a Lagrangian formulation. And so in this case, partons are represented by what's called a collinear modes in QCD. In other words, you have fields living on the light cone. And again, that n represents this light cone coordinates, and n squared equals 0. So therefore, you have fields living on the light cone. And this light cone distance lambda is a coordinate along the light from direction. And so the Parton physics is actually related to correlation of fields along those light cone directions. And in recent years, people have been using a new effective theory, dual perturbation theory, called soft collinear effective theories. And people have been able to do, 2 loop, 3 loops in this framework. And again, in those framework, the partons are represented by the collinear modes. Now, there is actually an interesting analogy between partons and critical phenomena. And many people probably know that parton distributions at very small x goes like x to the minus alpha. And alpha is some positive exponent. And so therefore, when x gets very small, the density gets very large. And if you go to coordinate space, it means that you have correlations around the light cone going to go like lambda to the alpha minus 1. So what does it mean if you have a system with correlations decays algebraically at a very long distance? It means that you have a system with infinite correlation. And if you talk about a condensed matter system, for example, the correlation usually decays exponentially, like e to the minus c over lambda. And c here is the correlation length. So if you have an algebraic decay, it means the correlation lengths go to infinity. And so the Parton system or infinite momentum frame actually corresponding to a system at a critical point in condensed matter physics. And of course, the new condensed matter theorists ever solve a critical point problem exactly at a critical point because the problem is too hard. So that explains that why, to some extent, why the light-fine quantization formalism holds so much promise, but it has never been successful. One may try to solve the Parton physics because it involves the light-fine correlation. You can try to solve it using quantum Monte Carlo methods. It has not been very successful because you have to deal with real-time dynamics. And again, you're talking about light cone correlations, and so therefore the real time is involved. And this is a oscillating phase factor and with an I, and it's numerically impossible to do at present time. It also goes under the name called a sign problem. And in condensed matter physics, the Hubbard model for high TC has a sign problem. And so nobody knows how to solve it using Monte Carlo simulation. And because the signals are exponentially small. And nowadays, of course, there's a lot of talking of solving a real Hamiltonian problem using quantum computer. And in fact, there has been a lot of work in, for example, solving Hubbard model using a quantum computer. There are also been discussions solving the Parton physics using a quantum computer. But I think, it's amazing that people are going that far. But I think it will take a while before we have a real solution to the problem. So what I wanted to do in the next section is talk about the original idea of Feynman, the Partons and infinite momentum frame. So the original Parton model of Feynman was used to describe the electron-proton deep analysis scattering. And again, it's textbook material. And it also happens in atomic or condensed matter systems, and where basically you knock out the electron in a system. And nowadays, for example, in condensed matter physics, you get ARPAS technology using the photon beams to knock out electrons and look at the spectrum of electrons. People would also do neutron scatterings under liquid helium-4 to measure the momentum distributions. Now, in those experiments in non-relativistic systems, as I said, they measure momentum distribution. So what is a momentum distribution? Let's consider a hydrogen atom, and you got electrons moving around. You wanted to know what is momentum distribution. Well, the answer is that you look in the Fourier transform, the wave function, then you square it, and that gives you the momentum distribution. And then if you expand this into the coordinate space wave function, and you discover that actually you're looking at a coordinate space correlation function. So you got a wave function at R and a wave function at 0, and you Fourier transform the correlation. If we move into a many-body system, you can turn this wave function into creation annihilation operators and take expectation values in the many-body ground state. So the upshot of this discussion is this. The Feynman got the Parton distribution from the momentum distribution. A momentum distribution is related to special correlations of fields, and these are Euclidean correlations. And so for Euclidean correlations, they should be solvable using classical Monte Carlo simulations. So what I'm saying is that the origin of the problem is not as complicated as we think. Now, what is the difference between relativistic and narrativist systems? And in narrativist systems, like in condensed matter or atomic physics, the energy transfer is very small because the energy transfer is related to the kinetic energy difference, and the kinetic energy is proportional to 1 over the mass. And when the mass gets very heavy, so the energy transfer equals 0. Now, in relativist system, and for example, in deep elastic scattering, in order to go to this normativist picture, you would have to choose a frame in which the virtual photon has 0 momentum. And that is possible. And relativity tells you can look at scattering any frame you like. And photons are space-like. You can always find a frame in which the energy equals 0. In this frame, you discover that momentum of the hadron is actually very large. And in fact, in the Bjorken limit, when Q goes to infinity, the momentum of the hadron goes to infinity. And so therefore, that we're going to follow Feynman's idea, that is, we consider a momentum distribution in the hadron with overall momentum equal to P, and you integrate out transverse momentum of the constituent. And however, this momentum distribution going to depend on how fast the hadron is moving, or what the momentum is. And that is because, unlike non-relativistic systems, the Hamiltonian doesn't change if we move the system with certain velocity. But for relativistic systems, the Hamiltonian doesn't commute with a boost. And so therefore, that the momentum distribution of a hadron does not stay the same. And Parton distributions is actually a result of the momentum go to infinity. So therefore, you take the limit of this with the momentum go to infinity, and you got the Feynman Parton distributions. Okay, so that's how the original concept of Parton distribution was derived. And you can see that in this original formulation of partons, and what you're really interested in is a spatial correlation of the fields. It involves no time, but you have an external state traveling with the infinite momentum. And you taken the limit such that the special correlation Z times the momentum, which I call the lambda, and this stays finite. So you have to take in a very delicate limit. And so you calculate the correlation function, and you Fourier transform this correlation function, you get Feynman Parton distribution. Okay, so this I call a infinite momentum frame formulation of Parton physics. Okay. Now, what is the relationship between these two different formulations of partons? So the textbook formulation is in terms of light-front correlation functions and involves time. And so it's very much like Heisenberg representation. And in this formulation, the matrix element is independent of external hadron momentum. And in this old-fashioned Feynman formulation of partons, and you use infinite momentum states to select the partons. However, the operators are very simple. They're Euclidean operators. And so this corresponds to Schrodinger picture of partons. And I have a simple picture to show the connection of these two. The blue curve here, the blue line here, shows the static correlation, which corresponding to the traditional momentum distribution. And then you can use Lorentz transformation to boost this correlation. As the hadron move faster and faster, this correlation become closer and closer to the light cone. And so therefore, basically, the two pictures are related by infinite Lorentz transformation. However, that the blue curve, again, is time independent. And so therefore, is possible to calculate or simulate using Monte Carlo, whereas the red correlation is along light cone. That's much more difficult to calculate. Okay, so that brings me to the large momentum expansion and effective field theory. Okay, so if you want to calculate partons using Feynman's approach, you want to take the infinite momentum limit, which is very difficult. And nobody knows how to create a hadron state with infinite momentum. And but let's assume that limit exists. Let's assume that, in fact, I will tell you later that this limit is actually quite subtle in the context of field theory. Let's assume that this limit exists, and we can calculate at a large, but not at infinity. So let's assume we're going to calculate a large momentum, pz, and we get a distribution. And we can expand this at pz equal to infinity limit. So the leading term here would be the Feynman Parton distribution. And then we have corrections, the power corrections. It goes like the hadron mass divided by the momentum squared. And so therefore, if this limit exists, and you can use a Taylor expansion to study this, this problem now becomes much simpler, okay? And the key thing is, how big is this expansion parameter? So let's call it epsilon. And let's do a naive dimensional analysis. And so you got a hadron mass divided by pz squared is an expansion parameter. The hadron mass is typically 1 GeV. So if a hadron moving at 2 GeV, then you got an expansion parameter as a quarter. And it's not, and 1/4 is not a bad expansion parameter, because, you know, people talk about large NC, QCD, and NC equal to 3 for QCD. And so 1/3 is already a good expansion parameter, and a quarter should be better. So that's kind of very naive thinking. So I proposed this in 2013. And the basic idea is that Feynman's Parton corresponding to momentum equal to infinity, but I can approximate it by large momentum. And in fact, it does not have to be very large. And that is what we do frequently in QCD. For example, in lattice QCD, we're trying to using a discrete space-time to approximate a continuum field theory. And we use a momentum cutoff, and which is equal to pi over A. A is the lattice spacing. And many people use lattice spacing of 0.1 Fermi that corresponding to a lambda equal about 2 GeV. So we're approximating a infinite momentum cutoff with a 2 GeV. Sometimes it's a very good approximation. Same thing with the heavy quark effective theory. And we have charm and bottom quarks, and charm quark is only about 1.5 GeV. And sometimes we can approximate by a heavy quark with infinite mass. And the trick here is that 1.5 GeV is a lot heavier than lambda QCD, okay, a lot larger than lambda QCD. So long as your scale is much bigger than typical hadronic physics scale, and this should be a good approximation. Okay, so I think my computer is frozen. I had to stop share. Sorry about that. My computer gets a little problematic. Let me try to share it again. Okay, so let's see if we can move forward. Okay. However, that this limit of PZ go to infinity has some subtlety in there. That's because QCD is a UV divergent theory, and you need to introduce a UV cutoff. And once you introduce a UV cutoff, the PZ go to infinity is no longer analytic because you're going to have log PZ in the calculation. So log PZ certainly is not expandable at PZ equal to infinity. I'm going to skip some of the technical details because in the interest of the time, already speaking 35 minutes. And so basically what I'm saying is that in field theory, this limit is much more subtle. And one limit is the momentum is much less than the cutoff of the theory. That is a limit actually you can do in lattice QCD. However, partons living in a different limit, that is when the momentum of the system is much bigger than the UV cutoff. And that's where you have partons. And these two limit, the difference of these two limit can be actually bridged by QCD perturbation theory. And the point is that the difference of these two limit is related to the high momentum modes of the theory. And we know the high momentum modes can be calculated in perturbation theory. And so therefore we can match these two different calculations. So if you know one answer, you can get the other answer by perturbative matching. Okay, so let me put all these into formula. So basically, I'm saying in order to calculate parton distributions, you can calculate a momentum distribution of a hadron with some large momentum PZ or moving with certain gamma factor. Then you can expand your calculation in terms of 1 over gamma. And if you have gamma equal to 225, it should be a pretty good expansion. But then the leading term is not exactly Feynman Parton distribution. You have to use matching, and there you have two different limits. You have to match it, but nonetheless, you get a well-defined formula. And the F tilde is what we call now quasi-distributions, and that is calculable on lattice. And F is the Feynman Parton distributions you want to get. Z is a perturbative factors you can calculate to order in perturbation theory. And then you have power corrections. And those power corrections are related to the size of the moment that you have, but also related to the fraction of Parton momentum. And as you can see that this calculation will not be very good if at y close to 0 or 1. So if you have partons moving very fast or very, very slow, that expansion is not going to be good. But it's the same thing as an experiment. You know, if you want to probe very, very small X partons, you need to go to very, very high energy. And same thing that in the calculation, if you want to calculate very small X partons, you need to create a hadron moving with large PZ. Okay, so in any case that this is the effective field theory formula for partons. And you can also have a momentum renormalization group equation, which I'm not going to discuss in detail here. Because as I said, that Hamiltonian doesn't commute with the boost, and so therefore the property of the system can depend on how fast the system is moving. You can write down renormalization group equations and to study that how the properties of the system depend on the momentum. Okay, so that's the momentum renormalization group equation. And that in the end actually gives the physical interpretation for the de Laplace evolution for the Parton densities. Okay, so the strategy of calculating Parton distribution in this way is very much like in condensed matter physics. And so here I show the 1 over the momentum, very much like a temperature of a condensed matter system. And P go to infinity is actually a critical point. And that is where you want to know the Parton distributions, and you don't want to calculate at that critical point. And the red region is where that the system can flow into the critical point under the renormalization group transformation. And so therefore, if you can study the system in the red region, and you can try to extract the critical point properties. And that's what people do in condensed matter physics all the time. And so you study systems close to the critical point. And because it's similar to critical phenomena, so you have the universality concept that is basically just like, in phase transition, whether you have ferromagnetic systems or you have liquid gas phase transitions, so long as they belong to the same universality class, they would have the same exponent, critical exponent. And so this effective field theory approach tells you that so long as the momentum gets very large, you can start it with any sort of operator and calculate Parton distributions. You have many different ways to get the same physics. I'm going to skip this, directly go to applications. So let me see, I have not much time. Okay, so I have about 10 minutes. Is that right? Okay. Just make sure. Okay. So I'm going to show you several applications very quickly. One is the Gluon total helicity, delta G. It's a light cone correlation function of Gluon fields inside of the nucleon. And Anish Manohar wrote down this in 1991. And it's a light cone correlations. And Brookhaven, in fact, spent quite a bit of money trying to measure this at Rick Kleider, polarized proton, and extract the delta G. But because of the light cone correlation, nobody knows how to calculate for many years. And so we propose using large moment effective field theory to calculate this. And I'm not going to go to technical details. In fact, this showing the universality phenomena, you can basically calculate E cross A in any kind of gauge you like. And the infinite momentum limit, you should get the same results. And the picture is very close to the Weizsäcker-Williams in Jackson's textbook. And so this is the first application of this LaMET theory. And so in 2017, the KCD collaboration took our approach, and they calculated for the first time the Gluon polarizations inside of the pore of the proton. And so this was selected as one of the 7 or 8 highlights of the year in 2017. The second application is actually to directly calculate the Parton distributions. And I had a specific proposals how to do this. And so there are people, this factorization theorem was proved to order in perturbation theory. And there are many groups around the world use that approach to calculate the Parton distribution. The ETMC is the European collaborations, LP3, and Zhengwei Chang, actually from National Taiwan University, played a very important role in the LP3 collaborations, and we published many papers. And then LPC collaboration, this is a new collaboration now in China, recently has done a lot of calculations. Anyway, I just show you that some of the results. This is the ETMC results published 2018. And the experimental curve is showing as purple and gray. And then this curve here is the best calculation run 2017. This is another calculation for polarized quarks inside a polarized proton. And this is the LP3 calculation also for the polarized quarks inside the polarized proton. And the red is the LP3 calculation results. The blue and green are the experimental Parton distributions. And this is the LPC, a group from mainland China has done calculations. This is, matching to the two-loop orders. And then generalized Parton distributions, that's something which has become a major program at Jefferson Lab, and also the future electron ion collider in US. And I'm not gonna go into great detail, just showing you that there has been some calculations lately using the approach, and there's much less experimental data on this quantity. I think it's critical that you can do lattice calculation for those. There has been a lot of studies recently about the transverse moment dependent Parton distributions. So again, I'm gonna be very brief on this. So there has been very successful formulations of calculation using lattice QCD, and there are two groups. One is my collaborators, and the other is the MIT group. And so we formulated factorization theorems, how to calculate since on lattice eventually can match onto the experimental TMD distributions. And so one thing I wanted to point out, this approach is not only you can do for partons, but you can also do any kind of, well, I wouldn't say any kind, you can certain type of light cone correlations. For example, the so-called softer factor represents, you got two opposite charged particle and radiate soft bosons, like gauge boson, photons or gluons, and the total cross-section of this is called a softer factor. And so we figure out how to calculate this using larger moment effective theory. And so this is a calculation for the evolutions of TMD distributions on lattice. And the curve here showing perturbation theory works for small BT, and for large BT, they cannot calculate. And so this is lattice data. And this is the cross-section of softer factor for two oppositely charged moving particles. And this is being calculated by a group in China. And by the way, this thing has just published in PRL recently. Finally, I want to say that this program can be used to calculate all the light front wave functions that Ken Wilson and Stan Brodsky wanted to calculate and couldn't. And for many years, they tried to get light front wave functions of a hadron by, Hamiltonian approach. And so far, nobody was able to even provide a close approximation to that. And the LaMET theory have a very standard way how to calculate this. And nobody has done that yet, but I'm sure people are going to move on to this very soon. So let me conclude. And So basically that here I identify an expansion parameter, which is lambda KCD over the momentum of the hadron. So long as this is small, you can do a particular expansion and resulting in a theory called a large momentum effective theory. And we're going into LaMET 3.0 right now because the initial test followed by a lot of activity showing one can get pretty good answer, but not in a precision error yet. And so in the next few years, we want to reach 5% precision with two loop matches, with momentum going as large as 3 GeV, with improved non-perturbative renormalizations. And in the long run, 10 to 20 years, and one day maybe we can claim 1% accuracy for the Parton distributions. That the picture I was showing you in the beginning of my talk, and I think probably with enough computational power, we can probably get even better accuracy than the showing in these curves. So thank you very much for listening, and this is the end of my talk.
You compute the fragmentation function in your formula.
Is somebody asking me a question? I have a little difficult time to hear. Maybe someone can refresh it when they're close to the mic.
Thank you for. Hi, can you hear me?
Yes, I can hear you now.
Oh, thank you. I want to ask a question about the. Can you use your method to calculate the fragmentation function?
Calculate what function?
Fragmentation.
No. I don't know how to calculate fragmentation function, which is a challenge.
I want to add another question. Is you mentioned you can calculate the TMD.
Yes.
So can you is a proof the fragmentation proof of TMD is hold or for
Yes.
order? Oh.
Yes. We have a paper which appeared recently and published and actually has been published showing the factorization proof for the TMDs. And so you can formulate quantities on lattice in Euclidean space, and then you can show that in the large momentum limit, you can get the experimental TMD distributions.
Oh, okay. Thank you.
Xiangdong had a question. Hi, Xiangdong. Nice talk. I have one question about the few figures you shown by lattice simulation on the method. So your theory is then supposed to be really everything is calculable, but then several groups still have differences. So what are the causes for the differences?
That's a good question. Actually, to make an ideal lattice calculation is a big challenge. Lattice has been around for several decades. Only in recent years, people can actually do calculations systematically connect to the physical points. That is, you have small enough lattice spacing, big enough volume, and you have small enough pion mass. So there's many criteria that you have to satisfy in the lattice calculation in order to be compared to the experiments. And so some of these calculations, they're not done in a physical point, and there can be finite lattice spacing effect. There can be pion can be too heavy, and so they're not exactly a physical world. So the point of these, however, is it can be improved systematically. So you can make a smaller lattice spacing, big lattice volume, and then you can see the improvement gradually. And that's the key point. And so that's why it will take time for people to get all these errors under control.
Okay, thanks. By the way, what is the LC3 collaboration which Junwei is in? Oh, LP3.
LP3. We call it a lattice Parton physics project.
Okay, so the collaboration is the worldwide, or which?
Well, actually LP3 no longer exists. We have formed the new collaborations. So LP3 existed for probably 5 years or so, and then people have different priorities, and we move on to different collaborations, mostly related to computer resources.
Okay, any other questions or comments? My question had been asked already, so no further questions. So we thanks Xiangdong again.
Okay, thank you.
Yep.